So I know we had the online test
Mhm.
um, this week. When is the next online test going to be?
That is one of the announcements I'm making is the next online test will be next week for you guys. I can probably allow it to spill over until the Monday the following week, but basically next week. My
Okay.
students are all doing it on Wednesday. So I have that time available to anyone that wants to take it at our campus during normal day hours where I'm there. Y'all can take it
Wait,
on
you're talking
Wednesday.
the online test or the test two?
It's actually both. It's going to be a face-to-face test that will be done next week. But like I said, you guys that are online, I probably allow till at least Monday, if not Monday or Tuesday, Monday and Tuesday. And there's an online test that'll be due that same day. So basically, whatever day yours will be due, uh, the online test will be due as well. So there's a face-to-face and a online test that will be due next week, possibly
Okay.
Monday, Tuesday thereafter, and it will cover everything up through 23 and 24.
Right. So it'd be I can't remember. Is it 21 to 24?
It would
Yeah.
technically be 17 to 24. All my
Oh,
tests are
right.
comprehensive, so there may be some material from thermo and all that stuff. I doubt it. Normally, what I do with that is if I saw something that was really bad in the last test that students were missing about thermo chapters, I might choose a problem like what students did badly on and put that on there. But other than that, normally my comprehensive tests just mean that guess what? You can't understand chapter 24 unless you understand 23, and you can't understand 23 unless you understood 22
Yeah.
and 21, that sort of thing.
Yeah. I mean, those all those chapters go in tandem with each other.
Yeah.
Um,
The practice tests have already been made, by the way. It's one practice test for both the online and the face-to-face one, and they were made yesterday.
okay. So that was going to be my next question. I don't know if you're going to do a practice test for the face-to-face. So you're lumping it in with the so essentially the practice test for the online test will be also be the practice test for the test two.
Exactly. Yes,
Okay.
and it's called. I'll look at the area right now. Well, actually, if I go to the right page, I will look at the and tell you the right thing. But I'm currently in the wrong page. Now I got like 20 tabs open because all good computer users have 20 tabs open. That's not it.
Yep.
That's not it. It's got to be somewhere around. I know I was just looking at where'd it go. Oh, nope, that's the wrong one too. And evidently, I've got 20 of the same one open, so that's even less helpful. Oh, yep, there's another one of that same one. I don't know what the heck I did with it. Anyways,
Yeah.
242 DO1. But it's in the practice test. It's listed
Yeah,
as
yeah,
like
yeah.
test five.
You're gonna open it up here shortly, I'm assuming,
Yeah,
like
it
this
it
week.
should be opened already.
Oh,
Hell, let
shit.
me just
I didn't
do
look.
this. I'm just gonna open it again because what's one more tab?
Yeah, not really.
Oop, there it is. Okay. So yes, if you look under practice test, you will see. Okay, it's not visible
Yeah,
here.
I was gonna say I see the latest is oh
Hmm.
wait.
What did I just finished making it and putting it up.
Oh no.
It's not here either. Oh
Well,
crap! I
if it's
probably put
not
it in
there,
a.
it's
I think
not
I put it in a
online.
lab course by mistake. It will be an online test as well as it will be in practice tests. And tomorrow, I promise, there will be no
Yeah,
drinking
yeah.
before class.
I'm not waiting with bated breath, trust me. It's fine. I trust you that you're on top of it,
I
but
did it all yesterday. So I don't even know where it went.
I believe you.
Okay. Well, I'll send out an email when it's done too, in case anybody sees this, so they'll know. In case they don't see it in time, anyways, I'll go ahead and email. So I'll let you know. But we should go ahead and get started. I'm going to start off. Normally, I try a little bit more robust problem than the one I'm getting ready to do. But sometimes when you work a more robust problem, it takes so much time and is so confusing that it actually makes it worse for the students. So that happened yesterday with my face-to-face class. So I'm going to go back and attempt a slightly easier problem to show you how to use the formulas for capacitors in series and capacitors in parallel. So what I'm going to do is give you a circuit. I'm going to go ahead and draw the circuit now. And basically what I'm going to have is a battery with a bank of capacitors connected to it. The battery, I'm going to say, has a voltage V0. And I know I'm not sharing my screen with you yet because I'm just
It's
working
fine.
through the simple part now of drawing it. So I'm going to go up and have a capacitance C1, which equals 1.00 microfarads. That's going to be in parallel with C2, that is 2.00 microfarads. And then those two will have wires that go back to connect to a single capacitor that is in series with that bank of parallel ones. That one's C3, and it's going to be 3.00 microfarads. And then that's the whole circuit basically. We're just going to allow it to come back and connect with the battery. So we basically just have three capacitors, and I'm going to work out the details of the equivalent capacitance, and then I'm going to work out the individual charges and voltages across each one. So I have it drawn now. I'm going to go ahead and share my iPad screen. I understand you normally have labs, so if you have to split, that's usually on Thursday, so isn't it?
No, that's today.
That is today. Okay. So if you
Yeah,
have to split,
Tuesdays.
it's not a big deal. I
Yeah, I'll
understand.
no, yeah, I'm gonna split 30 minutes before, so in an hour.
Okay,
Uh,
that's cool. So I got
gives me
some
some
time
time
with
to
you
get to.
anyways. Good deal. All right, so you see the capacitors I have drawn. Hopefully that's not too terribly unclear. What we do when we have a bank of capacitors like this, just like if we had a bank of resistors and we wanted to simplify that to one resistor, we just one by one go through any pair that match the definition. So we have a definition, for instance, we have solution that includes a definition C equivalent parallel is equal to C1 plus C2 plus dot 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 in the event that C1, C2, and so on and so forth are parallel. But if C1, C2, so on and so forth are in series, then C equivalent series, its reciprocal is equal to 1 over C1 plus 1 over C2 plus dot dot dot. So those are what I mean when I say if you find any two or more resistors, or in this case capacitors, that match the definition of parallel or series, then you go ahead and attack those. The order doesn't really matter as long as you are actually doing ones that do fit the definition. The order won't matter, and you just work it out. When we're done with that, we're going to actually figure out exactly what happens in terms of the charge, where it goes, how much charge gets on each capacitor, how much voltage does each capacitor have across it, that sort of thing. So what we're picturing here is I have a C1 and C2 that are in parallel. So I know for a fact I can say C equivalent, and I'll call it 1 sub 2, meaning the equivalent of C1 and C2, is just going to be equal to 1.00 microfarad plus 2.00 microfarad, which gives me, of course, 3.00 microfarad. That means my circuit is now, simplifying it quite a bit, we now have a single capacitor up here that is C equivalent 1, 2, and then a further along we have C3 that's in series with it, and that's our circuit now. Again, we have V0 as the voltage. In this case, we have two capacitors that are in series, and the formula for series is 1 over C equivalent. Now, this one will be the total equivalent capacitance for all of the capacitors, so I'm just going to call it C equivalent. So I know 1 over C equivalent is going to equal 1 over C equivalent 1, 2 plus 1 over C3. Well, 1 over C equivalent 1, 2 is 1 over 3.00, and 1 over C3 is also 1 over 3.00. So from that we get 2 over 3. So C equivalent would equal 3 over 2 microfarads, and that's 1.50 microfarads. So now we can finally say that that whole circuit is completely equivalent to a voltage V0 in series with a single capacitance whose capacitance is 1.50 microfarads. So that is our answer of this quote unquote simple
So
problem.
you add what's in series to what's in parallel to
Hmm.
get the okay. All right.
Yeah, so I first reduced the C1 and C2 and reduced it to a single capacitance. That was the 3.0 that we got.
All
That made
right.
it now that we had two in series, and the series formula is the complicated one with capacitors, but it's the simple one with resistors. Does that make sense?
Yes.
All right. So now going back to this, what I want you to understand is, according to the battery, it should know the difference between this bottom one, the middle diagram, or the top diagram.
All
And in
right.
fact, what we might think is that V0 is going to cause an amount of charge Q to go to the left. That's going to establish a certain amount of positive charge Q on the equivalent capacitance. That positive charge will build up on the left hand side, and that will compel the positive charges on the right hand side to flee. So they're going to run away. And then, in fact, what's ultimately going to happen is that same charge Q is going to come back in to the backside of the battery, or at least be equivalent to doing that. So from this, we know that the definition of capacitance, which is C equals Q over V, that was the other thing I was supposed to write down, C equals Q over V. From that, we know C equals Q over V, and this tells us, in fact, that uh, Q should equal C times V. So in this case, we're going to take the equivalent capacitance, which is the 1.50 microfarads, and we're going
Times
to
the
multiply it
voltage.
by the voltage. Now, just so we'll have a number, I'm going to go ahead and say V0 is supposed to be 12 volts. I didn't say that before, but I'm saying it now. So we'll just call that 12.0 volts. So now I'm going to write in, oops, I'm going to write in 12.0 volts. And of course, 1.5 times 12 is 18. So this is going to become 18.0 microcoulombs. And that's the charge that leaves the battery. So in terms of our second diagram, that means a charge of 18 microcoulombs goes around here, and then that establishes itself on the C equivalent. But that C equivalent's not a real capacitor. That's not one that really that we know anything about. We know about C1 and C2 making that one, so we'll deal with that a little later. But what we do know is when two capacitors are in series, that middle section, this part of the wire from here to
Hmm.
here, notice it includes the left side of the right capacitor and the right side of the left capacitor. That was just a piece of conductor that had no charge. But as soon as the charge plus Q got on the left hand side of C equivalent 12, that made the equivalent charge negative Q get on the right side of C equivalent 12. And then that left the right side of, or the right end of that wire, which is the left end of C equivalent 3. That made this one develop exactly the same charge. So over here, we're going to get that same charge of 18 microcoulombs on the left-hand side of C3, and then negative 18 microcoulombs on the right side of C3. So what that tells us is not only is Q, the total charge leaving the battery, 18 microcoulombs, but that means Q3 is also uh, 18 microcoulombs. So I can now say Q3, which is the charge on capacitance 3, is 18, oops, is 18.0 microcoulombs. So I'll sign that off, and I'm also just going to say that Q is 18 microcoulombs, so I'll go ahead and mark that as well. Now that we know what Q3 is, we can also figure out what V3 is, and that is done by using again C equals Q over V. So this is going to require us to say V is actually equal to Q over C. So V3 is going to become 18 microcoulombs divided by C3, which was 3.00 microfarads.
Parents.
Now we're starting to see how we can use the typical electricity and magnetism, or specifically the circuits type stuff, prefixes. We can just leave those prefixes in there a lot of times and let them cancel out and stuff like that. So the micro divided by the micro cancels out, and we get 18 divided by 3 gives us 6. Oops. Gives us 6.00 volts.
Oh,
So that's V3. And now I'm going to take a second and do something that I like to use in my circuits classes as well. I use something sort of like a little bubble, and what the bubble represents, it's a little bubble you can imagine sticking it anywhere on the circuit, and it'll pop up a bubble, and inside that bubble will say the voltage. It's sort of like electronic workbench. You can actually like take a probe and touch various places in the software called electronic workbench. It'll just tell you the voltage there or the current through it. So I'm doing that, but in order for you to understand what it means, what we're imagining is we normally take, if there's one battery, we'll put a ground immediately to the right of the negative side of the battery so that that has a voltage of 0. And then immediately to the left side of the battery where the positive terminal is, that voltage will be exactly equal to the voltage of the battery. So when I do that, here's what it looks like. I'm going to say right here, we have 12.0 volts. And again, what you're thinking is this is our multimeter. It's
right.
set to volts, and we have a red side that is V and omega, and we have a black side that is COM. And what I'm doing is I'm connecting the COM to right there, and I'm also attaching that to a ground. Then what I'm doing is taking the red and touching it somewhere. In this case, I touched it right to the left side of the battery. So that little diagram is really what's happening everywhere I put a bubble. So wherever I put a bubble, that's basically putting the red cord that's connected to V omega there. So what we just discovered was that the voltage across capacitance 3 was 6 volts. Now, if we go on the assumption that the resistance of the wire is negligible, then I think you'd agree that 0 volts is 1, since I put the ground right there at the negative terminal of the battery. You would agree that 0 is the voltage there, yes?
On the right side of the battery?
Yeah.
Yeah. I mean,
Okay. Yeah,
yeah.
exactly. And it's not always that way, but if you force the ground there, then it automatically makes everything sort of set up like the battery
Is it
meant it.
because the currents then just go into the ground rather than to the negative end of the battery?
That is actually a really good way of putting it. And I'd never think of it that way, but I did discover when I was reading Heaviside and Maxwell's work that that's the way they picture it. They never picture the current as coming back necessarily through the same wires. They expected it coming through the ground and back using the earth as a return path. But yeah, that's equivalent.
I mean, I always just think of like lightning, lightning
Yeah,
always has to find the easiest path
to the
to the
ground. Yeah,
ground.
exactly. So
Um,
since I made the argument that the wire had 0 resistance, then we'd really suspect that that 0 volts is also true right here. Does that make
right.
sense to you?
So, but then on the left side of C3 is 6 volts.
Exactly. So, and that's the key part that I'm trying to point out here. So if I draw this bubble over here and show it humps like that, then this will be 6.0 volts right here. So that's the left side. But that also means the 6 volts will also be right here and right here.
That's true.
Does that make
Okay.
sense?
Yeah.
And now you see that this means if we make the same assumption we did before, which is that the wire has 0 resistance, then you'd expect 12 volts to be the voltage right here and right here. Does that make
Okay.
sense?
Yeah.
So now that you see the voltage across C1 is 12 on one side and 6 on the other, and the same thing for C2 is 12 on one side and 6 on the other, you probably reach the conclusion that V1 equals V2 equals 12 volts. So we'll remember that, but we're going to compute it as well using our equations. But now we know what it should be, and we can check our work if we screw up. So what we do know is that 18 microcoulombs actually left the battery. So this is 18.0 microcoulombs. And I know I just drew that so small that no one in the world can read it. So let me undo all that.
But you said it.
Yeah, I said it. It should be enough, right? So 18.0 microcoulombs. That's a little better now that I'm writing it while it's big. Now I'm going to pull that. Now, what's going to happen is 18 microcoulombs will be split. Some fraction, let's call it Q1, will go that way, and another fraction, Q2, will go this way. But we know that Q1 plus Q2 has to be equal to Q, which is the 18.0 microcoulombs. Does that make sense?
Q1, yeah, plus two equals Q equals, yes. Yeah.
Okay,
Yeah.
so yeah, that's just a conservation of charge thing, right? Now, the other thing we know is that V1 equals V2. Can you see why we know that the voltage across C1 is equal to the voltage across C2?
So where's V1 and V2?
The voltage across the capacitor
Okay.
C1 and the voltage across the
And
capacitor C2.
yeah, yeah, I can see since Q1 and Q2 are, um, yeah, that makes sense. Okay.
Because they're in parallel, right?
Yep.
Because they're in parallel, V1 is equal to V2. And if we look at C equals Q over V, we can see that V is equal to Q over C. So V1 equals V2 tells us that Q1 over C1 is equal to Q2 over C2.
Q1. Yeah,
Okay.
because yes. Okay. All right.
Yeah, and now we can plug in the C's and we'll see Q1 over 1.00 microfarad is equal to Q2 over 2.00 microfarad. Now this means that Q2 is actually going to be equal to 2.00 times Q1.
Right.
Does that
Yeah,
make
because
sense?
you're multiplying both sides by two.
Exactly. So now we can take this part and put it in this part, and that'll give us the actual Q's. It'll give us
Okay.
Q1 or Q2. In this case, we're eliminating Q2. So if I put that in there, what I get is Q1 plus 2.00 times Q1
Q1, yeah.
is equal to 18.0 microcoulombs. So we end up getting that Q1
Q1 times three,
exactly is 3Q1 is equal to 18. So we divide both sides by 3. That gives us
three,
6. So
6.
Q1
Yep.
should be 6.00 microcoulombs. And that means Q2 should be 6 times 2, which would be 12.00 microcoulombs.
Are
So we
we,
now
do
go
we
ahead.
lose the units when we, on the step above that, when
Yes,
we,
the
do we lose the
microfarad completely.
microfarads?
Yeah, the microfarad and the microfarad cancel each other out when we solve for Q2 in terms of Q1.
Oh, that's true. Yeah, because it's inequality. Okay.
Yep. So now we can see that Q2 is 12 and Q1 is 6. And if we look back at our Q1 over 1 equals Q2 over 2, you can see that Q2 over 2 would in fact be 6 volts. And Q1 over 1 is also 6 volts. So we've now concluded that we were right when we did that little mechanism by figuring out that the voltage across C1 is 6 volts and the voltage across C2 is 6 volts. Now we can see it's right because clearly this gave us the same result. That back and forth and using multiple methods to look at the answer after it's done, that's what you want to do in these things so that you can always check your work.
Okay. Yeah.
Uh, so does that make sense?
Yeah. In principle, yes.
Okay. All right. So that's one of the ways we go about simplifying complex circuits that are just banks and banks and banks of capacitors. Luckily, we're not going to deal with too many circuits that have a bunch of capacitors in it, except to do these types of exercises. Okay. But there's a neat one your book does, and I like to do something just like it. So let me show you what we're going to do here. I'm going to take two capacitors and I'm going to imagine connecting them to a single battery source, but I'm going to do so in such a way that they're in parallel. So I'm going to take a power source. Let's say this is going to be, I like a nice even number. Let's say it's going to be 40.0 volts is V0. So I've got a 40 volt DC type of voltage source, and I'm putting it in parallel with two capacitors.
Okay.
One capacitor is going to have a capacitance C1 equals, let's say this is going to be, let's say this is going to be 20 microfarads, and I'm going to treat it as 3 sig figs, even though I only wrote it as 2. I'm going to say it's 20.0. Now, in addition to that, I'm going to have another capacitor over here, and that capacitor is going to be C2 equals, let's do this one. Let's call this one 10.0 microfarads. Okay. Now my plan is to take this battery and use it to charge these two capacitors up. These two capacitors are going to get a certain amount of charge on it. The amount of charge they're going to get is Q1 and Q2. And basically what's going to happen is we're going to get a certain number of plus symbols that come up on the top plate of C1, and then that's going to compel the exact same amount of negative charges to come up on the negative on the lower plate of C1. Now, in an attempt to make sure that these things have the same voltage because they're in parallel, that means the charge on C2 has to be somewhat different. So maybe I'll draw it as if it only has two positive charges and two negative charges over here. But the main thing is that V1 equals V2 is equal to 40.0 volts
So in
for
these
that.
schematics, out
Mhm.
of curiosity, does it matter the direction on the positive and negative charge on the capacitor?
No, there are some capacitors that occasionally matters which one you put towards the positive side and which one you put towards the negative side. But in general, capacitors, it doesn't matter too much, which side's which on a circuit diagram, for instance.
Okay.
Diodes are different though. Diodes, light emitting diodes, they usually have a one
Yeah.
direction is to turn on, and the other one is basically supposed to be a complete block, so that current can't go the other way. So that might be what you're thinking of too. Now that we have that, what we're going to do is bring up the charge, and what I want to know is what are V1, or excuse me, what are Q1 and Q2. That's part A. Now in part B, what I'm going to do is I'm going to take these charged capacitors very carefully now. I'm going to take them and put them, sort of reverse their polarity, if you will. And now it has a voltage V1 and a charge Q1, and this is capacitor C1. And then I have another one over here that is capacitor C2, and it has a voltage V2 and a charge Q2, like this. And only this time, Remember, I had C1 had like four positive charges on it and four negative charges on it. And now what I'm going to do is flip the polarity of C2 before I connect them. So that now instead of having the top on positive, it's actually going to be the top is negative and the bottom is positive, like that. And then I'm going to connect them. Okay. That's going to create a whole new system, and that system's going to look something like this, where this is still C1 and this is still C2, but now it has a charge of Q2 and a voltage that I'll just call V. Let's call it V prime actually. And this side will have a charge Q1 and also a voltage V prime. Okay. My job for part B is to figure out what are Q1, Q2, and V prime. Okay. So that's what we're going to try to work out. Solution. What we have to understand here is C is equal to Q over V. That's the defining equation for capacitance. C is the charge per unit voltage. That's one way of thinking about it. So we have to use that. We have to use the principles like, two things that are in parallel have the same voltage. Things that are in parallel, their currents have to add to give the net current, or things that are in series have the same current. Things that are in series have such that their additions are that their voltages add to give the total voltage. So we're going to use all that knowledge, but let's go ahead and just start with part A. So part A, what we found was that there's going to be a certain amount of charge that leaves V0. What will that charge be? Well, we can imagine it being a charge just plain Q, and this Q is going to go around here, and then it's going to break into Q1 and Q2. So what we could do is first find the equivalent capacitance of the two in parallel, and then figure out what charge that single capacitance would actually cause. But in this case, we can also do it just by realizing the fact that the two capacitors C1 and C2 are initially in parallel, so that Q1 over C1 is
One.
equal to Q2 over C2. So this way allows me to do it without first making it into a single equivalent capacitance and then solving for Q. But both ways are good, and it's not bad to try both of them to
You
check
mean
your work.
by adding 1 over C1 plus 1 over C2 is equal to, you
Yes,
mean doing it that
exactly.
way?
Well, in this
Okay.
case, they're in parallel, so it'd be C1 plus C2 is the equivalent. So it's actually really, really easy. Uh, in this case, we had 20 microfarads and 10 microfarads. They're in parallel, and remember, the parallel is the simple formula for capacitors. So
Ah,
this would just be the equivalent of 30 microfarads.
okay. I always get
So
the,
if you
I got, yeah. So
Yeah,
that's
so if you
parallel.
if you tried to find the charge, what you'd find is the total charge leaving the battery, Q, is given by C times V. Well, that C is now going to be 30 microfarads, and the voltage is 40. So 30 times 40 would be 1200. So that'd be 1200 micro coulombs is what we expect the actual charge to be. In this case, all we know is that Q1 over C1 is equal to Q2 over C2, and we know that Q1 plus Q2 has got to equal Q. So that's
Mhm.
actually enough for us to figure out what Q is either way. So I'm going to plug this in. I'm going to say Q. Whoa, Nilly. I'm going to erase a bunch of stuff because my program randomly turns into an eraser, and that's super helpful. So I'm going to say Q1 over 20.0 microfarads, remember, is equal to Q2
Two
over
over 10.
10.0 microfarads. So this time we get a little bit different scenario. We get Q1 is equal to 2.00 times Q2. Whereas
Okay.
before we got Q2's twice Q1. But that's okay. We have that. Now we can plug that back into our Q1 plus Q2 equation. So replacing Q1 with 2.00 Q1, or excuse me, Q2
Two. Yeah.
plus Q2 is equal to the total charge Q. We don't really know what the total charge Q is, but in principle, we could find it. Uh, this is the case where you realize that the voltage has to be equal to 40. So you
Right.
can say that Q is equal to, again, from C equals Q over V, Q is equal to CV. So I'm going to say it's equal to, uh, well, C would be, the equivalent capacitance, of course, would be 30.0 microfarads. And then the
Times
voltage would be
40.
40
Yeah.
volts. That makes sense.
Yep.
So the 3 times the 4 gives you 12, and that gives you 1200. So what we have is 1200 microcoulombs
Coulombs.
is equal to 2, or is equal to 3 Q2.
Right.
Because
Yeah.
2, yeah,
And simplify it.
exactly. So now we can figure out that Q2 must be equal to 1200 divided by 3. That's
400.
400 microcoulombs. And then, since Q2 is actually supposed to be half as big as Q1, then we know that our Q2 is supposed to be, yeah, Q1 is supposed to be twice as big as Q2. So we can now say that Q1
Q1 is 800.
is 800
Yep.
microcoulombs. So now we have that part of the answer worked out for part A. I did end up using the equivalent capacitance, but I was thinking there was another way I was going to do it where it didn't, and it just escaped me for a split second. So if I don't know if I actually knew another way or just forgot, but that's okay. We got the first part solved. Now here's the tricky part. What we know is going to happen is we're going to take 800 microcoulombs and have it on the left. So we now know this is 800 microcoulombs, and we know this one is now 400 microcoulombs, and we're going to put them in contact with each other. So notice I'm going to get 800 positive coulombs is going to touch 400 negative coulombs, so that you're going to get the new charge, which will be Q1, say, that new charge is now going to be given such that 800 minus 400 is equal to the original. So now that we're doing that for part B, what we're going to say is Q1 plus Q, or excuse me, I should say Q1 minus Q2 is going to be equal to the total charge Q. It might help you to realize that these are sort of in series now. There's really no other way of thinking about it, and so doing that'll make a little bit more sense to you. But ultimately, what happens is Q1 minus Q2 is
Right.
now
Yeah.
equal to.
Hold on.
Go
On
ahead.
that thought. Yeah, because it's essentially it's a closed circuit, and you're talking about with that next diagram. If you
What's
connect them, they're on a closed circuit and they're almost acting in series at that point rather than
exactly?
parallel. Okay.
Yeah, that's a way of thinking about it. Another thing you can think about is the whole top half is all one big conductor, so it has to have the same voltage. And then when you look at it this way, the whole bottom half has to have the same voltage. So in that sense, they actually have the same voltage. So they're in series in some sense, but really right now you see that they're in parallel. You understand how I made that argument? Because the top is one continuous conductor, it
Wait,
has to be an equal
point to what you
potential.
mean the top and bottom. Are you talking about that second diagram there?
Yeah, so
Ah,
this part.
that diagram. Okay.
Yeah, so this, and this are all one continuous piece of conductor. And
Right.
conducting surfaces are equal potential surfaces. Equal
Right.
potential means equal voltage. So the whole top has one voltage and the whole bottom has another voltage. In that sense, they're actually parallel.
Right.
Okay. So that's why I was able to say there's a single voltage for the two that I called V prime. Okay. Now, what we do know is that Q1 minus Q2, because we've reversed their polarities, one of them's going to win. The one with the biggest magnitude is going to win the sine war. So the 800 wins the sine war. And since I'm looking at the top half, that means the positive 800 wins the sine war. And you have to subtract from it positive 400 to get obviously positive 400. So now we can rewrite this equation here as 400 microcoulombs is equal to Q1 plus Q2 because all that charge is going to distribute itself in some way that the voltage of the top is going to be equal to the voltage of the other part of the top, and the voltage on the bottom is going to be equal to the voltage of the other part of the bottom, so that the two voltages will be equal. So
Okay.
we now have this equation, which I'll call, let's just call this equation one. I should have been numbering these before, but I didn't. Like when I was doing this and this, it would have been smart for me to number them so you could see that I actually used this to get this, but then I plug this into that. That would be a lot more easily understood if I had used numbers and said I'm doing this and that. But anyways, I didn't do it. So I now have equation one that tells us the relationship between Q1 and Q2, which I'm trying to get. But I also have another relationship that says V prime is equal to lowercase q1 over c1, and that's equal to lowercase q2 over c2. So with that, I can go ahead and write Q1. There I go again. My calculator, my program just changing it. Q1 over C1, which is 20.0 microfarads, is equal to Q2 over, in this case, it was 10.0 microfarads. So we can again say that Q1 is going to be equal to 20.0 microfarads over 10.0 microfarads times Q2. This is what we were talking about earlier. Everything cancels out, including all the units. So you get the microfarads canceling out,
You
and you
just get
literally just get a factor of 2.
two. Yeah.
So that means Q1 is equal to 2.00 Q2, and I'm going to call that equation 2. Now I plug, whoa, now I learn how to spell plug, which starts with a P and an L, not a P and a U. Plug 2 into 1, and what happens there is we get Q1 plus 2.00 Q2. Ah, crap, there I go again. I keep making a careless mistake when I'm not paying attention to that. So Q1 is what we're replacing. So in place of Q1 in equation 1, I'm putting, dang it, there I go again. In place of Q1, I'm putting 2.00 Q2 plus Q2 is equal to 400 microcoulombs. So we've got 3Q2 equals 400 microcoulombs. That means Q2 is 400 divided by 3. That would be 133.3. So this is going to be 133.3 microcoulombs. And then, of course, we now have Q2 is this. And obviously that's an extra digit beyond the sig figs, that 3 that I have there. But now we can use the fact that Q1 is twice Q3 to say that this is going to be 266. So Q1
Yeah.
would be 266.7 microcoulombs. And now that we have those two charges, we can figure out what the new voltage is. Do you think the new voltage will be lower or higher than the 40 volts we had before?
Oh gosh. I don't even know. I can't.
I was exactly the same way. The only thing that made me think of it is uh, I pictured that when I disconnect the battery, I'm not going to get any more energy from somewhere, and I'm probably going to lose some energy by the
Right.
charges canceling
Yeah.
each other out. So I suspect the voltage would be smaller. All we
Right.
really have to do is say
But
V prime,
there's
which
gonna be
we know.
some magical reason why, in those instances when I think of a logical reason why it would be that way, it'd be like, nope, it's the opposite of what you're thinking.
Exactly. Well, that's exactly what we try to do as teachers, just to make sure you're not learning anything in any particular time. I'm going to
To really
choose.
confuse you.
Yeah, I'm going to choose Q1 over C1 for this, but we could have used Q2 over C2. Q1, of course, was 266.7 microcoulombs, and then C1, we know was in fact
Yeah.
20.0 microfarads. So 266 divided by 20
Funny.
gives me 13.33 or
Yep.
133. Is it 13?
13, yeah. 266
13.
divided by 20 is 13.3.
And that is the actual voltage. So the voltage went down a lot. The voltage went from
So it
40
went from
volts
40
to,
down to 13.
yeah, that's a pretty big hit. But that's a typical problem that your book would like you to understand. And the main thing is just trying to get some feel for what's going to happen when you take a capacitor, put it in a circuit, and then connect a battery to it. We know if you have a series of series capacitors, then each capacitor is going to have the same amount of charge across it, but their individual voltage will be different because each one has a different capacitance. And the
Right.
total voltage has to add up to be the voltage of the source if you're just doing any number in series.
So
So
capacitance is the stored energy.
yeah, we can use it as a stored energy source, but it also has an analogy in when we studied last semester in 241, you studied the transfer of energy back and forth between kinetic and potential on a pendulum, for instance, or on a spring on a
Yeah.
mass. Well, it's going to turn out that when we make a circuit, energy is going to slosh back and forth in exactly the same way as it sloshed back and forth between kinetic energy and potential energy. It's going to slash back and forth now between magnetic energy that's going to be due to an inductor that we'll learn about later and electrical energy that's going to be due to capacitors.
Okay.
So that's ultimately where it goes. And that's part of the reason why we spent so much time studying harmonic motion because lo and behold, the differential equations look exactly the same. So hopefully that'll give you a little bit of forethought of what's coming when we get to AC circuits that include not only resistors and capacitors, but ultimately inductors as well. Have you run into inductors before? Do you know what inductance is?
Um, like you mean practically what they are?
Yeah, like far as a particular item in a circuit would be, or what the
Uh,
concept of induction is. You don't have a.
I I can't think of anything. I mean, if you can give me an example.
Yeah, I figured I didn't think you had any electronics experience, but sometimes you say things that suggest you did, so I didn't know if you actually
Well,
knew
I
it.
did wire up a camper van,
There you go.
and I did have to deal with AC and DC circuits, but it was a matter of, someone kind of guiding me
Helping you,
on
yeah, helping you
how
not
to
kill
wire
yourself.
everything up.
Yeah,
I
exactly.
mean, it's just put this here, put this there, you'll be good.
Have you stayed overnight in a Holiday Inn hotel?
Uh, I trust my electrical work on the van more.
Gotcha. Uh, yeah, that's one of the running jokes is I stayed in a Holiday Inn Express, so now I know how to do surgery on the brain. All right, so let me show you what we're going to talk about here now. So we have these capacitors, and we figured out how they behave. What we're going to do now is we're going to try to make some sense of them, and I'm going to show you that they in fact do store energy. As I said, they are, in some sense, an analog to either potential energy or kinetic energy, and then the inductance is an analog to the opposite one. What I was referring to, far as induction goes, often you'll see something that looks like a solenoid in electronics.
Yeah.
Any solenoid looking thing is an inductance. Or if you see a little loop with wires wrapped around it, like a donut, like if you wrapped wire around a donut,
Yeah. Okay, I
that
just
would
looked
be
it
an
up.
inductor.
Yeah.
Okay.
Okay.
Not only that, the fact that we now can take our smartphones and lay them on their back and get charged, that is due to
Right.
inductance. That's specifically what we call mutual inductance. And that's what we're going to learn once we figure out things about the magnetic field and how to calculate magnetic fields. I'll, just like we did before, I'll introduce this new object, and the object will be called an inductor. But we'll start off with studying mutual inductance, where basically if you have a coil of wire carrying a changing current, and you have another coil of wire near it, there's some chance that even though those two coils aren't touching via conductor, the conductor that has a current going through it that's changing will create a current in the other inductor, even though it has no power source.
Huh.
And that's what, that's why we can now charge our cell phones by laying them on their back.
Yeah, wirelessly.
Yep.
Huh.
So kind of cool, huh? All right. So far as storage goes, remember work is equal to the integral of F dot dl. That's what
DL.
we learned the previous semester. But we also learned that we could, for instance, uh, we could actually use it like this, where we would take into account instead of force, we might say, well, force is equal to Q times E. And then you'd say QE dot DL, and then you could look at that and say, okay, well, how is this related to anything? Well, what we discovered is E dot DL is actually the voltage. So we can actually flip this and call it the integral of V dq. Notice how we just chose to take the differential. It could have been on the L, it could have been on the E, it could have been on the Q. What we did was absorb the EDL and made that what would normally be like a dV, and we chose to make the D on the Q instead. So in doing that, we can take capacitance definition, C equals Q over V, to conclude that, oops, I don't want that one. We can do that to conclude, for instance, that V is equal to Q over C. So if we put that in, we're going to get the integral of Q dq over C. So you see what I did? I just replaced the V with a lowercase q, just so it would match the dq that I already had there, over C, because that's the formula for capacitance. And of course, this gives me 1 over C, and then the integral of q dq is 1 half q squared. So what we found is the work done in charging up a capacitor is q squared over 2c. And that is a appropriate formula. I usually use capital letters, so what I'm going to say is this work is also equal to a potential energy. I don't want to use a delta there. I'm just going to use a plain U. So that work can go into establishing an amount of energy that we can treat like a potential energy, just like, sticking an object on top of a pole gives it a potential energy. Charging up a capacitor gives it a potential energy. Does that make
Yeah.
sense?
Yep.
So now that we have that, we can say U is equal to Q squared over 2C, which is my least favorite of the formulas, by the way. There's three of them getting ready to give you, but this is just the ugliest
The
one, and I hate
least
it.
favorite.
It's my least. You've got to have opinions on all these things. Like, 37 or 73. 73 is clearly the better number. That sort of thing. All right, so now if I use C equals Q over V again, I can also get that Q is equal to CV. And doing that, I'm going to replace the Q squared with C squared V squared over 2C. Now we're talking business. This is the one I like. So you see this is going to cancel out with this, and we're going to get 1 half CV squared.
Yep.
Notice that looks just like 1 half MV squared.
Ah, okay.
But it also looks a little bit like 1 half kx squared, which is also going to be relevant. So
Jeez.
now we've got
It
two
all
forms.
ties together, is what
It
you're
all
saying.
ties together. It's some beautiful tapestry.
Yep.
Okay. So there's two forms, and there's one more form as well. Right now we've got Q with C, we've got C with V. Now we need Q with V. So what I'm going to do is use C equals Q over V to rid myself of the C. So in this case, I'm going to say, oops. In this case, I'm going to say 1 half, and then C is Q over V times V squared. So in this
Right.
case, you can
B's
see that
cancel out. So one
e-
half QV.
exactly. So you get QV over 2, and that's the third version. So ultimately, our result should be U is equal to 1 half CV squared. It's also equal to 1 half Q squared over C, and it's also equal to 1 half QV. And that's the various versions of energy stored in a capacitor.
Huh.
That makes sense?
Yep.
So I will go on, and what we're going to do, and I know you're going to have to leave pretty soon, so that's cool. But I'm going to continue
10
working
minutes.
here. I want to show a use of this. So, for instance, we might want to know how much energy can be stored in a capacitor. Uh, so I'm going to do that by wording a problem like this. So here's our example, and what we're saying is how much energy can be, whoa, can be I don't know where that came from. Can be stored in a 500.0 microfarad capacitor uh, if it is connected to a 200.0 volt power supply. Whoa, let's just call
Jeez.
battery. Okay.
Oh, pack a punch.
Yeah, yeah, I can give it a whole bunch here. So, and as I told you, 1 farad capacitor would be dangerous. So, this is not going to be a 1 farad capacitor, but covering at 200 volts and 500 microfarads, that might be enough to do some bad stuff. So, our solution is we need to know C equals Q over V, maybe, but we're definitely going to have to know U is equal to 1 half CV squared, or 1 half Q squared over C, or 1 half QV, one of those. What we're going to try to do is I have been giving a voltage and a capacitance, so I need the C and the V formula. So I'm going to
Right.
say U is equal to 1 half CV squared. That's going to be 1 half 500. And remember, I'm just adding that so everybody knows that I'm using 3 sig figs. So it's 500 microfarads times, in this case, it's going to be 200.0 volts. That's going to be squared.
Where, yeah.
So we can say, if my calculator will ever turn on, zero point 0.5 times 500 times 200 squared is a butt ton. One, two, three,
Yeah. What? How many
four,
zeros?
5, 6, 7. So 10 to the seventh is
Yeah.
equal to 1.00 times 10 to the seventh joules. So the energy stored U is equal to 1.00, or actually, we can do it a little nicer. We can say it's 10.0 megajoules. Okay. So that's the energy stored. And remember what I told you guys, a joule is about as much energy as required to lift a red delicious apple from the ground or from the floor to the top of a dining room table. So we're talking enough to lift 10 million apples.
Yeah. A lot of apples.
Yeah, and I suspect if someone threw 1 million apples or 10 million apples at you fast enough to get there, that might kill you. So
Yeah.
I,
Yeah.
I would assume the electricity can do the same thing, so I would not haphazardly touch this. Another thing that you want to learn, though, about this is it turns out that the quantity R times C actually has units of seconds. So that's a good exercise for you to practice, using some of your former equations that define what the resistance is and what the farad is. You should be able to show that that is a unit of seconds. And that is the characteristic time. When we actually start studying capacitors in a circuit, we'll learn that that's a time constant. And basically, R times C is the amount of time it takes to go from 0 to roughly or 1 over E times the total voltage it's going to reach. Stuff like that, where E is that 2.71828, the base of the natural log system. So, anyways, that comes in handy. And in fact, we're going to call tau the characteristic time or the characteristic capacitor time. Okay, so that's just another piece of information I wanted to give you because we're going there, obviously. Now, if you want to think about what happens when you separate, because this is some of the concepts of it. You can think about taking two capacitor plates and charging them up, getting a charge Q on it, and then taking and separating the plates. One, is that going to require work or is it going to do it on its own? If you just, for instance, allowed two plates of a parallel capacitor to get charged up, would they naturally be attracted to one another or would they be naturally repulsive of one another? Can you
Um,
think of that?
well, if it's, I'm gonna say it, take a guess. What, attracted, since there's a positive and negative on either side.
Exactly. Yeah, they are attracted to one another. So if you wanted to separate the plates to make the separation larger, you're going to have to put some work in.
Yeah.
So what happens when plates of a capacitor are separated? So what we can imagine is that we have a parallel plate capacitor represented here like that. We're going to say this distance right here is D. The capacitance, of course, is going to be just C equals epsilon 0 A over D, where A is the surface area of the individual plates. And what we're going to do now is we're going to take these same parallel plates and pull on them until instead of a distance D apart, they're going to be a distance 2D apart.
Right.
So it looks something like this. Oops, I went too far on this one. Yeah, that was supposed to
All
be.
your fun angles, you should get isometric paper.
Yeah, this
Draw
is
this to
driving me crazy.
scale.
Yeah, almost to scale. But I screwed it up a little bit and hit the wrong corner. So there we are. So now what we're doing is a distance of 2D, again, still with the same
Same
area.
area.
And now the capacitance would be epsilon 0A over 2D. So that's and I don't know why I subscripted epsilon with an A instead of, well, I do. My brain just decided to do what it was thinking of, which was the next step. So that's what really happens. So you might want to know how has the energy changed? Well, a lot of it depends on whether you keep the battery or not. So what happens when the plates of a capacitor are separated? And I specifically mean what's happening to the energy. So if, whoa, that's a neat new word I just made up. If the battery is first disconnected before separating them, the plates, then because the battery's been disconnected, the charge has nowhere to go. It's nothing it can do. The charge has to stay there. Then the Q cannot change, but the voltage can. Okay. So, so we had U equals, let's say, 1/2 CV squared. That's the one I like because it looks like all the other forms of potential energy that we deal with. So if I use that, I can see that something happening here, but it doesn't necessarily allow me to say that the charge is going to remain. So I could also use 1/2 Q squared over C, but I could also use 1/2 Q V. Double checking my formulas, Q squared over C, QV. Yes. So with this in mind, what we want to know is what happens to the energy when I do that. Well, the capacitance C, by going from D to 2D, the capacitor goes from C to 1/2 C.
Yep. Yep.
But the voltage cannot change, or excuse me, the charge cannot change, but the voltage can. So what we're going to see is by assuming the energy U equals 1/2 CV squared, that's one way we can look at it. Or we can look at the energy being 1/2 Q squared over C. I'm hemming a little bit here because hemming and hawing because I'm trying to remember what I was going to do with this. But but what we have is the C went down by a factor of 2. What's going to happen with the voltage? Well, the voltage, remember, is the integral of E dot dl. That's the way we normally compute that. And in this case, as long as the D is not too terribly large, the electric field is a uniform. So what happened is we got an electric field that didn't depend on distance. In fact, the electric field was sigma over epsilon naught. And by moving the plates further apart, it's still sigma over epsilon naught. So the electric field is going to stay the same, but the voltage, V, is going to have to go up by a factor of 2.
Yep. I was just thinking it has to double.
Yep. So the voltage is going to go up by a factor of 2, and the capacitance went down by a factor of 1/2. That means, oops, that means the energy U is going to be 1/2. Let's say U prime, because this will be the new value, and this would be U0. So U0 would be 1/2 CV squared, whereas U prime is going to be 1/2
One.
C over 2, but then 2
Yeah,
times V.
it's just CV squared.
Exactly.
Yeah.
So we're cutting it down by a factor of 2, but we're multiplying it by a factor of 4. So ultimately, it just increases by a factor of 2. So it's going to be 2 times U0. So increasing the distance between them actually increased the amount of energy stored. And you might think, well, did we just make energy? But
Yep.
your answer
We
that you
created.
go ahead.
No, I'm joking. I'm saying yes. Yes.
Yes, yes, we did create. Well, in some sense, we did because, as you told me, you said that it would actually take some energy to pull those two plates apart. So, if I were to grab those two plates and pull them apart, I had to do work on the system. And if you calculate exactly how much work is done, you'll find out, lo and behold, that exactly equates to why the energy went from U to twice U. So, whoop, therefore, the capacitance went down by a factor of 2. The voltage went down, or excuse me, went up by a factor of 2, and the charge was unchanged. so that U went up by a factor of 2. Okay. And that was with battery disconnected.
Okay.
If the battery wasn't disconnected, what would happen is that would lock down the actual voltage, but the charge would change. The capacitance would still go down by a factor of
Right.
2. So you look at, for instance, the middle equation. You look at this version now, and the capacitance went down by a factor of 2. That means the energy is going to go up by a factor of 2. The charge, on the other hand, because you're spreading it further and further apart, the charge is actually going to change in this case, but the voltage is staying the same because we're connecting it to the battery. So to do that, we're actually going to get a change in Q, and that would require another calculation. But it's just something to think about. So whenever you have the battery connected, remember it locks the voltage down, but the charge can change. But if you have the battery disconnected, then it doesn't allow the charge to change, but it does allow the voltage to. Does
Huh.
that make sense?
Yes.